Okay, now we are back again, right. So, up to equation 5 we have seen. Next is your that subscript I told you that 0 is used to indicate the pre-transient conditions, right. This applies to all machine rotor angles and also to the network parameters, since the network changes due to switching during the fault, right. Now, equation 4 can be written in the form x is equal to, actually that it will be x dot, right. A dot is missing, it will be x dot, right. X dot is equal to f x comma x 0 t. I mean, this way we can write, right. It is basically, this is for my own reference. So, x dot is equal to f x x 0 t, right. This way we can write, where x is a vector of dimension 2n into 1. Because for each machine you have two variables, right. For example, omega 1 delta 1, omega 2 delta 2 up to omega n delta n, this is equation 7, right. So, x dash is equal to transpose, right, and it is a, and this is actually x dot, there should not be any mistake, x dot, it is somehow a scanning thing, the dot is missed, right. So, now next one is that classical model of a synchronous machine may be used to study the stability of a power system for a period of time during which the system dynamic response is dependent largely on the stored kinetic energy in the rotating masses, right. For many power systems, this time is on the order of 1 second or less. Now, input data, what are the input data required, right. First thing is a load flow study of the pre-transient network to determine the mechanical power P m of the generators and to calculate the values of E I and that angle delta I 0 for all the generators. This is, I mean, a load flow study is required before fault, right. The equivalent, from that you have to calculate P m and E I angle, your what you call E I angle delta I. Actually, it will be in general that P m I 0 equal to P I 0, right. The equivalent impedances of the loads are determined from the load bus data, right. So, that we will see later. The inertia constant H and direct axis transient reactance x d dash for all generators, these data are required. One is inertia constant H and the x d dash, this is required, and R is very small, so neglected, right. Now, that is for generator. Transmission network impedances for the initial network condition and the subsequent switching, such as fault clearing and breaker reclosing, right. So, I mean, all these impedances, transmission network impedances are known because you have to compute that Y matrix that is before fault, that is pre-transient condition, during fault also you have to calculate, and post fault also, right. Now, number 4, the type and location of disturbance, time of switchings and the maximum time for which a solution is to be maintained. These are the input data before writing the code, although we will not learn code here, right. Now, initial calculations, what are the initial calculations required for transient stability studies? All system data first converted to a common base, that means convert to a common base, that means per unit system, right. The loads are converted to equivalent impedances or admittances. The data for this step are obtained from the load flow study, that we will see later, right. If a certain load bus has a voltage V I tilde, suppose now if a certain load has a voltage V I tilde, the complex phasor quantity, real power P L I, reactive power Q L I and load current I L I tilde flowing into a load admittance say Y L I is equal to G L I plus J B L I, then we can write P L I plus, this you know from your load flow studies, then we write P L I plus J Q L I is equal to V L I tilde, then I L I tilde conjugate, right. Or if you write P L I minus J Q L I, then it will be V L I tilde conjugate, then I L I, the way you write, right. So, now this one your what you call, then I L I is equal to your Y L I V L I, right, and Y L I is equal to G L I plus your J B L I. Therefore, your I L I conjugate, right, because here we need I L I conjugate is equal to your Y L I conjugate, then V L I conjugate, right. Or we can write this one that VLI conjugate, right, and YLI conjugate means it is YLI, and YLI conjugate means it is GLI minus J BLI, right. So, if you made it, it will be GLI minus J BLI, right. So, that is why this ILI conjugate is actually VLI conjugate into GLI minus J BLI, and here it is written ILI is equal to YLI VLI, right. So, ILI conjugate is this one, right. Therefore, your VLI tilde into VLI conjugate will be simply VLI square, because it is magnitude, right. So, therefore, PLI plus JQLI is equal to VLI square into GLI minus JBLI, right. So, that means we can write GLI minus JBLI is equal to PLI plus JQLI upon VLI square, right. Or if you take your what to call that conjugate on both sides, so that is why it is writing GLI plus JBLI, and this side we are writing PLI upon VLI square, this plus because of conjugate right hand side it will become minus. So, minus JQLI upon VLI square is equal to say YLI conjugate. This is equation 8, if both side you take the conjugate, right. Therefore, your that means from here you will get GLI actually is nothing but PLI upon VLI square, and BLI will be minus QLI upon VLI square, right. So, the internal voltages of the generator say EI angle delta I 0 are calculated from the load flow data. These internal angles may be computed from the pre-transient terminal voltage V angle delta as follows, right. Suppose it is E angle delta dash, right, and this is your XD dash, R is neglected, this is I angle theta dash, and this voltage V angle alpha is equal to V angle 0. Earlier we have seen that this if we change the if we change this thing, for example, if this side is minus, suppose it is E, my angle was say delta 0, right. Now, as this side, if we make it as a reference, instead of V angle alpha, if we make V angle 0, so naturally this side will be delta 0 minus alpha, right. That means if I make it like this, that means my delta dash will be delta 0 minus alpha, right. So, earlier also we have seen for the synchronous machine studies, right. So, that is why the meaning is that when I write V angle delta is equal to V angle 0 means it is not like alpha is equal to 0, we are changing the reference. If this is V angle 0 degree, then this side angle will change, right. So, that is why we will take this terminal voltage V as a reference, right. Therefore, so this is generator representation for computing delta 0, later it is given, right. Now, let the terminal voltage be used temporarily as a reference. I told you V angle 0 as shown in figure 2, this V angle 0, but let me tell you that it is a reference. If you shift the reference from V angle to that, this alpha here, this side has to be subtracted. Meaning is very simple. For example, suppose this is your reference line, this is reference line, right. Now, suppose it is your, for example, suppose this is your alpha, right, and this is your V, and suppose this is your E, this is your E, right, and this angle, say for example, this angle is your say I can make it say your what to call delta 0, right. So, this your what to call this angle, this is my reference, this is V, and this angle is your what to call delta 0, right. So, with better you take with respect to reference delta 0, right. So, this angle will be delta 0 minus alpha, right, this angle will be delta 0 minus alpha. So, that means with respect to V, with respect to reference, this angle is alpha, and with respect to this one, this angle was delta 0, that means this complete angle was delta 0, this was nothing, right. So, that means the angle between E and V will be your what you call delta 0 minus alpha. Therefore, if you take now your V as a reference, same thing, and if it is your E, then angle between these two should be delta 0 minus alpha. This is what I wrote earlier, that if it is alpha, if it is delta 0, if it is angle 0, it will be delta 0 minus alpha, right. So, that is why. So, now define now I tilde is equal to I 1 plus j I 2. So, this is actually say real part and this is imaginary part, right. Now, we know P plus jq is equal to V tilde I tilde conjugate, or P minus jq is equal to V tilde conjugate into I tilde. So, I tilde is equal to P minus jq upon V tilde conjugate, right, or I is equal to, we have assumed I 1 plus j I 2, that means I 1 plus j I 2 is equal to P minus jq upon V, but we know that your V tilde angle V tilde conjugate is equal to V angle 0 is equal to V. That is why this one directly we have written as a V. This is actually V as a reference. If we take, it makes our computation easier, right. So, it will be P minus jq upon V, right. Now, since that E angle delta dash is equal to V tilde plus j x d dash I tilde, that means if you come to this, it is E angle your delta dash is equal to I tilde j x d dash, right, plus V. So, here also we are writing the same thing, that E angle delta dash is equal to V tilde plus j x d dash I tilde, right, or E angle delta dash is equal to V plus j x d dash, and substitute whatever we have got just now, that I tilde is equal to P minus jq upon V, right. Now, you just multiply, then you will get E angle delta dash is equal to V plus j x d dash P upon V plus x d dash q upon V, right, or E angle delta dash, right, is equal to V plus x d dash q upon V plus j x d dash P upon V. This formula we need for computing the E value. Later we will see when we will take that your what you call that some problem. So, this is my equation, this is our equation 9, right, and earlier I told you that delta dash will be is equal to delta 0 minus alpha, that means my delta 0 will be delta dash plus alpha. Now, the initial generated angle was delta 0 is then obtained by adding the pre-transient voltage angle alpha to delta dash. So, delta 0 will be your delta dash plus alpha, this is equation 10, right. So, this is how I told you earlier. Now, so this equation 9 will be required for some computation of E and angle delta dash, right. Now, the Y tilde matrix for each network condition is calculated. The following steps are needed. The equivalent load impedances or admittances are connected between the load buses and the reference node. Additional loads are provided for the internal generator voltages, that is node 1 to n. We have seen in the figure 1, right, that general equivalent on transmission system load and the machines, right, and the appropriate values of x d dash are connected between these nodes and the generator terminal, your what you call nodes, right. Now, also simulation of the fault impedance is added as required and the admittance matrix is determined for each switching condition, right. Now, number 2 is that all impedance elements are converted to admittances, because we have to consider, we have to compute Y matrix, no, that is why we have to make it in terms of admittances, right. Now, number 3, elements of the Y tilde matrix are identified as follows. YII tilde is the sum of all the admittances connected to the node I. This you know from your load flow studies, and Yij tilde is the negative of the admittance between node I and node j. That is why in the load flow studies that your what you call in that Y matrix, that we use capital Y11, Y12 like this, but when we find out the admittances, diagonal admittances, all y small y are added and all your off diagonal elements capital Yij is equal to your minus of small Yij, it is negative of that, right. So, that you have studied from the load flow studies, that you know. Now, finally, eliminate all the nodes except for the internal generator nodes and obtain the Y tilde matrix for the reduced matrix. Ultimately, what will happen, that you have to reduce the Y matrix, that your order should be, if you have n number of generators, then it will be n into n matrix, right. So, that you have to reduce. So, you have to reduce by some technique that we will see. The reduction can be achieved by matrix operation if we recall that all the your what you call nodes have 0 injection current except for the internal generator nodes. We will assume in all the load there is current, no current in, I mean 0 injection of the current, right. That means 1 to n generators current injection is there, but rest of the nodes where generators are not there, the current injection will assume it to 0, right. This property is used to obtain the network reduction as shown below, right. Now, we know that in general I is equal to Y V, right. So, look, it is phasor quantity, but again and again I have not made it tilde, but understandable, all these are phasor quantity, right. So, all these are phasor quantity. Now, that your I is equal to it can be written I n 0, that means suppose you have n number of generators. So, all the generator buses you have that your current injection I n, right, and all other buses, load buses, all current injection is 0. That is why in general this I n and 0, right. So, I n means I 1, I 2, I n. If you have 3 generators, then n will be 3, right. Therefore, this Y matrix, right. So, that means we know this I is equal to Y V and I is equal to I n 0, then this can be left hand side I can be replaced by I n and this 0, and this Y matrix can be partitioned, that is you can make it partition like this Y n n, then Y n r, then Y r n, Y r r, that V n is that I told you that V n is that you have n number of generators. So, V 1, V 2, V n, and rest are all the load buses, right. So, it is up to V r, then the figure 1 we took 1 to up to r buses, the load buses. So, this equation 12. So, this way we can write this equation, I partition Y n n, Y n r, then Y r n, Y r r, this way you partition the Y matrix, right, and this is V n, this is V r. When we will take a few examples, at that time we will find things are very easy, right. Now, n denotes the generating nodes and r the remaining nodes, right. So, now from this equation you can write I n n, I mean you can write two equations. From this equation you can write in matrix form, of course. I am just writing like this, I n is equal to Y n n V n plus Y n r V r. This is one equation, I mean I n is equal. Another equation will be 0 is equal to, I mean this side is equal to Y r n, Y r n, then V n, right, plus Y r r V r, 0 is equal to, this is one equation, this is another equation, right. So, from this this is the first equation, this is the second equation. From this equation you can write Y r r V r is equal to minus Y r n into V n, or V r is equal to minus that Y r r inverse Y r n V n, right. So, this V r you got, this V r is equal to minus Y r r inverse Y r n V n you got, and this V r V r is equal to this one, you substitute here, right. Then what we will get, if you substitute, you will get I n is equal to Y n n V n minus Y n r Y r r inverse Y r n into V n, right. If you substitute here, then what you will get, I am just overwriting that I n is equal to Y n n V n. Now, you substitute here, so it will be, because of minus it will be minus, then Y n r, then Y r r inverse, then Y r n, this V n, right. If you take your V n common, right, then it will be Y n n minus your Y n r, right, then Y r r inverse, then Y r n, then V n, right. So, it will this matrix actually reduction to your n into n, right. If you, I mean it will be n into n matrix, I mean number of generators of n, so it will be n into n matrix. So, that is why here we are writing, if you substitute you will get I n is equal to Y n n, whatever I showed, minus Y n r, Y r r inverse Y r n into V n, right. This is equation 13. Now, this is actually reduction. So, all these things have been done. We will take a small example, right. I hope everything is readable. This is scanned copy of my notes. So, x 1 is equal to line impedance is given, reactance rather R is neglected, J 0.40 per unit, right, and it is a double circuit line, and x 2 is equal to J 0.40 per unit, both are same, right, and this is actually x d dash is equal to J 0.20 per unit, and this side nothing is given, right. So, we have to find out that your I mean pre-fault, your what you call then fault and post fault Y matrix, right. First we will see you see how we are doing it. Now, first what you do is that this and where fault actually for this problem not shown, I will tell you fault actually a 3-phase fault has happened in between in the middle of the line, second line, that circuit 1, this is my circuit 1 and this is my circuit 2, right. So, in middle of the line a fault has occurred, right. Now, that we will see later. Now, that when we represent this and x d dash is given J 0.20 per unit, right. Now, when we made it in terms of your admittances, so it will be 1 upon x d dash, so it will be minus J 5 per unit, right. Similarly, if you put in admittance, it will be 1 upon J 0.4, so it will be minus J 2.5 per unit, everything is per unit, and this one also minus J 2.5 per unit, right. So, in this case pre-fault, if you first we will represent by small y, the way you do load flow studies. So, y13 that is your y13 that is 1 2 3, right, it is minus J5 is equal to y31, right. Now, y32 right, y32 is equal to y23, it is your what you call it is a double circuit line. So, y32 minus J5, because these two will be added, these two will be added, right, it is the admittance one. So, that is why it is minus J5, right, because we have converted that reactance to your what you call susceptance, or in general we will call that is it is your admittance, right. Similarly, then your y11 then will be only minus J5, that your what you call y11. Similarly, y12 no connection between y12 is equal to y21 is equal to 0, because no connection between 1 and 2, no direct connection, right. And y13 is equal to capital Y13 will be minus Y13, right, minus Y13, that is your J5, and only diagonal element all small y will be added, or capital Y will be minus, right. And Y21 also no connection is 0, and Y22 that is your Y22 that will be minus J5, because this one minus J 2.5, this is minus J will be added because it is admittance, right. And y23 is equal to y32. So, y23 is equal to y32 is equal to minus small y32, that will be J5. This is my your what you call pre-fault your Y matrix, right. This is pre-fault Y matrix. Now, this matrix I have shown later, but in the terms of this thing, similarly y31 one thing is left. Similarly, y31 is equal to minus capital Y31 is equal to minus small y31 is equal to J5. That means, we know that y13 is equal to y3 minus J5. So, when we make off diagonal elements, so capital Y31 will be minus small y31 is equal to J5, and capital Y32 will be also J5, right, because 3 to 2 and this will be added and it will be minus small y32. So, it will be J5, and y33 will be minus J5 is equal to minus J10 is equal to minus J10, right. So, this matrix form I have shown later, right. So, this is all Y matrix, this you know how to calculate, right. Now, this Y actually it is your what you call minus J5, then 0, then J5, then 0, minus J5, J5 and minus J10, right. So, now in this case what you do is, so if you look into this, that y11 is minus J5, so minus J5. Now, y12 capital Y12, right, is equal to y21 21 is equal to y12 is equal to 0, then y13 capital Y13 is equal to your what you call 3 1 is equal to j 5. So, it is j 5. So, y your 2 1 is equal to y 1 2 is equal to 0. So, y 2 1 here it is 0, right. Then y 2 2 is equal to minus j 5, right. So, y 2 2 we have given, that is your what you call that y 2 2 means here, right. Y 2 2 means only these two, minus j 2.5 minus j 2.5, right. So, that is actually here is a minus j 5. So, minus j 5 and y 2 3 is equal to y 3 or 3 2 capital Y, this one is equal to minus small y 3 2 is equal to j 5. So, this is j 5, right. And last one y 3 1 is equal to minus small y 3 1 j 5, right. Similarly, y 3 2 is equal to same as j 5 and y 3 3 minus j 5, this is minus j 10, right. So, now you have in this example you have two machines, that is why this is 1 and this is 2. So, its partition should be like this, right. So, this is actually your YNN 2 into 2, n is equal to 2, right. YNN YNR, this is YNR, right, and this is YRN and this is your YRR, only single element here in this case, because in the classroom we cannot take very big examples, but certain thing will be shown, right. So, this is YNN, this is YNR, right, this one I told you, and this is YRN I told you, and YRR is a single element minus j 10, its inverse will be just 1 upon minus j 10, right. Now, we know this, that I put y dash is equal to YNN minus YNR YRR inverse YRN, right. If you substitute, if you substitute all this value and if you simplify, you will get y dash is equal to minus j 2.5, then j 2.5 and j 2.5 minus j 2.5. This is actually that your what you call that your pre-fault matrix, but reduced to 2 into 2, because you have two machines, right, you have two machines, right. So, this is your what you call that your pre-fault 2 into 2 matrix, right. Now, for fault case, a fault has 3-phase fault has occurred here in the middle of the your line, this second line, right. In the middle of the line, a 3-phase to ground, 3-phase ground fault has happened. That is why, as it is admittance, that whole line admittance was minus j 2.5, right. But now it will be minus j 5 because it was j 0.4 that your reactance. Now, if it is the middle of the line, so this side reactance will be j 0.2 and this side will be j 0.2. So, it is 1 upon j 0.2 will be minus j 5 and this side also will be minus j 5, right. So, based on this one, right, we have to find out that your first 3 into 3 your matrix during the fault case, then again we will reduce it to 2 into 2, because we have two machines, right. So, thank you very much, we will be back again to solve this.